in that case, I'm going to ask you guys some questions. So I'm going to have you, for yourself, take a moment and define oxidation and then define reduction. What is oxidation and what is reduction? Oxidation is a half reaction in which electrons are what? Yeah, it is. It's a loss of electrons. So a half reaction in which electrons are lost. My chat keeps disappearing off my screen every time I touch my screen. I'm not sure why. So if it takes me a moment to respond to your chat, it's because I keep having to pull the dang thing up again. And reduction, on the other hand, is a half reaction in which electrons are gained. And if we take those two and we put them together, we will get an overall reaction. So if we add these two together, we're going to get an overall reaction that is called a redox reaction. And today we're going to be focusing on putting those two together to get the overall redox reaction. But before we do that, we're going to just take a look at a few examples and decide, maybe in a fairly quick way, whether these are oxidation or reduction half reactions. Okay, so just take a look at A and B and see if you can determine quickly, without balancing it or anything, whether these are oxidations or reductions. Hi, Jason Chow. So that iodine going from I- to I2, what kind of a half reaction is that? And how are some ways we could tell? Well, we could take a look at our oxidation number. For iodine, we have a -1, so its oxidation number is -1. And for I2, that is an element on its own. Elements on their own, their oxidation number is 0. So we went from -1 to 0. So this became more positive. In other words, the number got larger, the oxidation number got larger. And if the oxidation number gets larger, that is going to be an oxidation. You can think of it from another perspective as well. This one's really easy because there's no like funny elements in there. It's just iodine. Iodine starts with extra electrons and it finishes with no extra electrons. So it must have lost electrons in the process. Going from a negative charge to a 0 charge means that it lost electrons, okay? We could do the same thing for Cl2. We could say that it has a 0 charge here because it is in its elemental state, all on its own. And over here, it has a -1 charge. Well, the oxidation number here got smaller. The oxidation number got smaller. In other words, the oxidation number was reduced, got smaller. being reduced means you get smaller. And since the oxidation number was reduced, it must be a reduction half reaction. Okay. Now, you could, if you didn't feel comfortable doing the oxidation number method, you could balance this thing. Just like we did last week, we could balance this half reaction. We could say Cl2 goes to Cl minus, and we balance our major atoms, which is non-oxygen and hydrogen. So that is we have a 2 here, so we need a 2 here. We balance oxygen and hydrogen, of which we have none. And that is major OH says charge. And so we add electrons, and because electrons are negative, we add the electrons to the side which is more positive. So because we have 2 negatives over here, we need to add 2 electrons to this side, so there's a 2 negative charge on both sides. You need to make the charge on each side equal. Once you've done that, you can see the electrons are going in. The electrons are going in. In other words, Cl0 does not have those electrons. The Cl minus does contain those electrons. And so if the electrons are going in, the substance is gaining electrons. And if it's gaining electrons, that is reduction, because of course Leo the lion says grr. Okay, I don't know if I left enough space for these. I might rewrite this one down just a little bit lower. Oh, and I didn't. No, SO2 goes to H2 SO4. Okay, so now we have one here where we have NO going to NO2. And I'm going to show you a quick little trick. Nitrogen has more oxygens attached to it than it did in the reactants. Okay, over here we have O2, and over here we only have one O. If it's something as obvious as that, and it doesn't have all kinds of, you can see down in the next example, we've got oxygens, and we've got oxygens, but oh gosh, we also have hydrogens, which makes it a little more complicated. But if you only have a single element and it's attached to oxygen and then it's attached to more oxygens, can you guess if that would be oxidation or reduction? If you go from having less oxygens to having more oxygens, is that oxidation or reduction? Yeah, it's oxidation, okay? So anytime you see that and you have less oxygens going to more oxygens, that's going to be oxidation. And we can prove that to ourselves either by balancing the half reaction or by looking at the oxidation number. So let's do the oxidation number method first. O, of course, is -2, and that means that N has to be +2 in order to give us an overall charge on that compound of 0. O is -2, but we have 2 of them, so that's going to be times 2 is -4. I would normally write this out properly, but I didn't leave enough room for myself. -4. And that means that the nitrogen has to be +4. And when the oxidation number gets bigger, which is what it did here, that is oxidation. Okay. The other way to do it would be, if you didn't like that method, you could balance your half reaction. You would have NO goes to NO2. I balance my major atoms, in this case nitrogen. Hey, they're already balanced. I balance my oxygen by adding water, H2O. And I balance, let's see what's left, hydrogen by adding H+. I've got 2 hydrogen on the left, so I need 2 H+ on the right. And then finally, I balance the charge. The charge on the left-hand side is 0. The charge on the right-hand side is 2+ because of the 2 and the plus. So I need to add electrons to the side, which is more positive. And so over here, I need to add 2 electrons. And you can see we have lost electrons. And losing electrons, of course, is oxidation. So many ways to prove that one to yourself. You've gone from less oxygens to more oxygens. That's called oxidation. If the oxidation number gets bigger, that's oxidation. If you balance it and you see electrons coming out, you have lost those electrons, losing electrons. Leo, losing electrons, is oxidation. Okay, now just to prove to you that it's not always that lovely, you can see over in our next example, we have O2 and we have O4. Well, it looks like we have more oxygens. However, it's a proportional thing, yes? Over in our previous example, we had N with 1 oxygen, 1 N to 1 oxygen, and we had 1 N to 2 oxygens. Yeah, so the ratio is different between N and O. However, in part D, we have 2 oxygens for every 1 nitrogen. That's a 2 to 1 ratio. And over here, we have a 4 to 2 ratio, which is a 2 to 1 ratio. And what that tells me is if the number of oxygens per nitrogen didn't change, my oxidation number is not going to change either. So this is neither an oxidation nor a reduction. Neither oxidation nor reduction. But if I want to prove that to myself, I can look and I can say I have 2 oxygens. Oxygen has an oxidation number of -2. So that means the oxidation number of oxygen is, well, it's -2 times 2, and I get -4 altogether. That means the nitrogen has to be +4. Over on the right-hand side, I have -2, but at this time I have 4 of them. So that's an overall negative charge of -8. And now I have to take that -8 and distribute it over 2 nitrogens. Well, I need a +8 to balance that out. And I need to take my +8 and distribute it over 2 nitrogens. So that's going to be a +4. So you can see that the nitrogen has not changed oxidation number. And so it's neither oxidation nor reduction. Okay. And actually, I think I'm going to leave that here for today. We are going to, we'll also look at it again in the context of this. We're going to look at balancing full reactions. In the assignment today, which I haven't posted yet, I will do so just like 5 minutes after our meeting here. In this handout, you'll notice when I have it, I've got big blanks and I'm going to write stuff in. You can feel free to copy along with me when I get to this example. However, the handout that you're going to get, this is already filled in for you anyway with all the various steps. So you can decide whether you want to write it down or not. Okay, so just for this part, just watch and follow along. Here I have a half reaction. So we have 3 electrons coming out. The electrons come out, and therefore, because the electrons are coming out, it is an oxidation. You can see that the oxidation number got bigger. It went from 0 to 3+. We have another half reaction here, and we go from having a 2+ oxidation number to a 0 oxidation number, and the electrons are going into the reaction, and because they're going in, we are gaining electrons, and so that is the reduction half reaction. Now I can actually put aluminum together, aluminum solid, aluminum 0, and I can put it together with copper 2+, which would be in solution, aqueous. And I would do a demo of this if we were at school, and maybe if I'm really clever, I'll find a video of it for you and post it with the assignment. You can put these two things together, and what you'll see is you'll see a chemical change. Copper 2 is a blue ion. Okay, it's a really lovely color. It's a little bit darker than that, but that's the highlighter color I have. And over time, what you're going to see is you'll see aluminum foil. We'll throw it into a blue solution, and over time, the solution will turn colorless. And that's because the copper 2+ is turning into copper solid, which has a 0 charge, and the aluminum is turning into aluminum 3+. Okay, which has a 3+ charge. And so this is an overall redox reaction. We've combined these two reactions to get an overall redox reaction here. And aluminum is a colorless ion. So we go from having a blue solution to having a colorless solution. And this is a silver metal. And this is a reddish metal. You know what copper looks like, reddish metal. So you'll see the silver metal will go away. You'll have red stuff in there, and it actually looks more red than copper does normally, but it is copper, and we'll get this colorless. However, we have a little problem here because nature does not like an imbalance of charge. Nature always wants everything to be neutral, because if you have a buildup of negative charge, those negatives are going to repel each other, and that is unstable. And nature's like, no, no, please, please, please make sure I have the same amount of positive and negative charge everywhere. So if we have aluminum giving off 3 electrons, but copper is only taking 2 electrons in, that means that we would have, you know, over here, we would have also as a product, let's see, 3 electrons coming out. That's from here. And we would have 2 electrons going in, which would mean that we could actually cancel 2 of those, but we'd be left with this like spare electron. And a spare electron in a redox reaction is a no-no. It's not like your half reactions. Half reactions will have electrons in them. Redox reactions will have no electrons. Half reactions, electron, yes. Redox reaction, electron, no. So we're going to have to worry about balancing out these electrons. We're going to have to make sure that we get the correct number of each. And so what we're going to do is we are going to, before we actually combine these two into something that looks like that, we're actually going to make sure that the number of electrons going in is the same as the number of electrons coming out. And we do that by finding the least common multiple or lowest common multiple of the two electron numbers. And we multiply each half reaction so that the number of electrons going in equals the number of electrons going out. So if we take a look at, let's see, if we take a look at this one here, we have 3 electrons times 2 is going to give us 6 electrons. And if we have 2 electrons times 3, we're going to get 6 electrons. But we can't just multiply the electrons, we have to multiply the whole reaction. So we have 2 aluminum instead of just 1 aluminum, gives us 2 Al3 plus because instead of just 1, and it gives us those 6 electrons. We have 3 times 1 is 3 copper. We have 3 times 2 is 6 electrons, and we have 3 times 1 is 2 coppers. Once we have made the electrons in equal the electrons out, we can add the 2 together. Okay, so we're going to write them one on top of the other. And we're going to add them up. And remember, we're going to have our 6 electrons out equaling our 6 electrons in. And just like in math, when you add equations, if you have something on one side of an equation and something on the other side of equation, what can you do with them? If you have something on one side of an equation and something on the other side of an equation, what can you do? Yeah, you can cancel them out. So boom, off they go. Okay? And then we just add up the 2 equations. We have 2 aluminum, 2 aluminum. We have 3 Cu2 plus, 3 Cu2 plus, 2 Al3 plus, and 2 Cu. And that is our overall redox reaction. How many electrons do I see in that overall redox reaction? How many electrons do I see in that overall redox reaction? None, absolutely. You should never see any electrons. No electrons ever in the overall redox reaction. No electrons left over. So you should see no electrons in the redox reaction. Okay. Okay, the number of atoms, if we actually have an overall balanced redox equation, it should fulfill 2 things. It should have the number of atoms of each type should be the same. Let's check that. 2 aluminum. Oh, look, 2 aluminum. That's good. Yay. Just like before, grade 11, grade 9, whenever you did that. 3 copper, 3 copper. That's fantastic. But the other thing that you'll see here is that the charge, the overall electrical charge, should be equal on both sides. And let's take a look at the overall electrical charge on both sides. We have 3 times 2 is positive 6 on the left, and we have 2 times 3 is positive 6 on the right. Yay, that's what we want to see. We want to see the overall charge being balanced. So if I just brought back to what I wrote earlier, maybe I'll rewrite it because it was so ugly. I wrote all over it. I had Al solid plus Cu 2 plus gives Al 3 plus Cu. You might look at that, and if you're in grade 10 or 11, you would say, hey, yeah, we're balanced. right? I have the same number of coppers on both sides. I have the same number of aluminums on both sides. But now in grade 12, you're going to look at that and say, but hey, watch out. 2 plus does not equal 3 plus. So the charge is unbalanced. That means this is an unbalanced redox reaction. And we need to be able to balance an unbalanced redox reaction. So let's go do a wee bit more complicated example of that. Here are the steps, the rules to balance overall redox reaction. Step number 1, you're going to have to isolate the 2 redox reactions. Step number 2, you are going to balance each half reaction separately. Step number 3, you're going to make sure the electrons going in equal the electrons going out. And then finally, you're going to add them back together. Okay, so, and then you will cancel if necessary. And finally, you can make it basic with hydroxide, just like you did with half reactions, making them basic. You can make overall reactions basic. So we're going to do, actually, I've changed my mind. We're going to do one example. I'm not actually going to have you do this worksheet this week. I'm going to have you practice a little bit more on the half reactions and on the oxidation numbers and on recognizing whether it's oxidation or reduction. And then we'll finish this up next week, because otherwise our lesson's going to go really long and I don't want to do that to you on a Pro D day. Okay, so let's just do one example to see what it looks like. Step number 1, isolate the 2 half reactions. So you're going to look and you're going to say, oh, Mn3 plus must be turning into MnO4 minus. Mn3 plus must be turning into MnO4 minus. It's as simple as that. Okay, you just look and you say, these both contain Mn. That must be one half reaction. My other half reaction has to be the gold half reaction. Okay, I'm not going to have gold turning into manganese. That's like some weird alchemy stuff from the Renaissance or something, you know, the Middle Ages. We don't want that. We don't want gold turning into manganese. We want gold turning into a different oxidation state of gold. So our other half reaction will be Au3 plus going to Au. So step number 1 is isolate the half reactions. Okay. Step number 2, you are going to balance the half reactions. Okay, and in balancing the half reactions, you are going to take a look and just do it like you did last day. Maybe I didn't leave enough room. Oh, that's okay. I'll pretend I did. Okay, so we're going to balance it now. This is step number, maybe I'll write it in blue. Step number 2, balance the half reactions. Manganese and manganese, there's the same number on each side. Major atoms are taken care of. After the major atoms comes O, which we balance by adding water, H2O. How many do I need? I've got 4 oxygens, so I need 4 waters. Then I'm going to balance hydrogen by adding, I've got 8 hydrogens, so 8 H plus. And then remember to calculate out your charge on each side. On the left-hand side, we have a 3 plus charge. And on the right-hand side, we have 8 positive and 1 negative. So 8 positive plus 1 negative is 7 positive. So my right-hand side contains more positive charge. I really did not leave enough room here. Let's fix that. Positive 7, there we go. So my right-hand side has more positive charge, so I need to add electrons. How many electrons do I need to add to the right-hand side? Yeah, I need to add 4 of them because that is going to be -4 added onto 7 is going to give me +3, just like the other side. So that's going to be 3 electrons. Okay. And then our next one isn't so messy. It's really easy. I've just got gold. There's no oxygen or hydrogen to worry about. So I'm just balancing charge here. So that's going to be +3 electrons because I've got 3 positive and 3 negative gives me 0 to equal the 0 of the gold on that side. All right. So step number 1, isolate the half reactions. Step number 2, balance the half reactions. So step number 1 is something new. Step number 2 is just what you did last week. It's just you're doing 2 of them instead of just doing 1 of them. Step number 3 is to make the electrons in, did I write 3? I meant to write 4 here. There we go. Make the electrons in, electrons going in equal the electrons going out. So you don't have any leftover electrons either not being used up or being produced. Okay, so let's rewrite this. So we have 4H2O plus Mn3 plus goes to MnO4 minus plus 8H plus 4 electrons. All right, and then we have Au 3 plus 3 electrons goes to Au. We make the electrons in equal the electrons out by finding the lowest common multiple of the electrons. So we have a 4 and we have a 3, and the lowest common multiple of 4 and 3 is 12. The LCM of 4 and 3 is 12. Once we've found that, we multiply the half reactions, take the whole thing and multiply it to give you 12 electrons. So the first reaction I have to multiply, what do I have to multiply the first reaction by? To get 12 electrons in that first half reaction. Yeah, I have to multiply it by 3 because I've got 4 electrons, so I need to multiply this one by 3. And for the second one, because I have 3 electrons, I need to take this whole thing and multiply by 4. Okay. And now I am going to multiply it out. And if I could show you my finger, I would actually show you that I put my finger on the 3, and then I put my finger on the 4, and I say 3 times 4 is 12 H2O. You can't see my finger, but you can see me writing, okay? And then I literally put my finger on the 3. 3 times 1 is 3, Mn, 3 plus. Why do I put my finger on it? So I don't forget to multiply one thing as I go through this whole mess, because I'm really bad at forgetting things. And then I have 3 times 1, MnO4, so that's 3 MnO4. And then 3 times 8 is 24 H plus 3 times 4 is 12 electrons. So that's my first half reaction. My second half reaction, I have 4 times 1 is 4 Au3 plus 4 times 3 is 12 electrons. And then I have 4 times 1 is 4 Au. So I have made the electrons in equal the electrons out. Step number 4, I'm going to add them up, add them back together. I separated my oxidation and my reduction. Yeah? Just before we go, let's take a look at our manganese, just before we go to our last step, I mean. Take a look at manganese and decide, without looking at the electrons or anything, do you think that's an oxidation or a reduction? Manganese 3+ goes to MnO4-. Yeah, it's an oxidation. And you can tell that because we just threw a whole bunch of oxygens on it. It got oxidized by the oxygen. Okay, you could calculate out the oxidation number, or you could look at it and say, I have lost 12 electrons. Losing electrons is oxidation. For the gold, you can look and say, I went from 3+ to 0, which meant that my charge, my oxidation number was reduced. It got smaller, so that is reduction. Also, we are gaining electrons, so that's reduction. All right, almost last step here. We have 12 electrons canceling with 12 electrons. So we're going to now have 12 H2O plus 3 Mn2 plus 4 Au3 plus. Okay, so I've done 12 H2O plus 3 Mn2 plus 4 Au3 plus goes to, now my products, I have 3 MnO4- plus 24 H plus. So that's done, and now I need to do plus 4 Au. And there are a few more steps that we might have to do next time, but for today we're done because if I look from side to side, there's nothing to cancel out. The only thing you're also going to do is you're going to check. You're going to check and say, hey, 12 times 2 is 24 hydrogen. 24 hydrogen, good, good. Hydrogen's good. 12 times 1 is 12 oxygen. 3 times 4 is 12 oxygen. Oxygen's good. 3 manganese, yeah. And 4 gold, yeah. And then the last thing you have to check, or maybe the first thing, sometimes I get lazy and I just check my charge. And if my charge works out, then I'm like, oh, I'm probably pretty good. Over here we have 3 times 2 is positive 6. And over here we have 4 times 3 is positive 12. And on the right-hand side, we have 24, positive 24, and we have 3 negative. Did I do this right? Or did I go wrong somewhere? Oh, it's Mn3 plus. Oh, 9. There we go. That's better. Okay. I'm like, my charge isn't working. What's wrong with it? So we have 9 and 12 is positive 21. And you see how by checking my charge, I noticed that, oh, I wrote the charge wrong. And over here we have negative 3 and 24, which, oh, thank goodness, is actually equal to 21. Okay. So I'm going to, this week, you're not going to do this worksheet, okay? I'll put it up there just so that you have like a tidy copy of it rather than this nonsense. So if you want to take a look through it, you can, but that's not going to be the homework this week. The homework this week is going to be number 1. Let's see, oxidation number worksheet, oxidation number worksheet number. So this time we'll do what? 21 to 25, 5 questions, that'll be fine. Number 2, you're going to do the half reaction worksheet. 6 through 9. Yeah, come on. 6 through 9. And you did, what did you do last time? 12 through 14 and 15 through 18. Okay. And last but not least, the third thing you're going to do is going to be a third thing, but you'll have to wait until see it on the assignment. I'm not going to make you sit here while I try and sort myself out, although I did that for a little while and I am very sorry. So I will see you next Wednesday at 9:30. Okay, so this will be a bit of a light time. I know some of you have just finished up AP exams and you could probably use a little time to catch up on things, and maybe you're just needing a long weekend too. Okay, so next Wednesday at 9:30, and yeah,